So it's 2 o'clock now, so we can get started. And today we are really honored to have Professor Jason Kong coming here to give us a talk on space and time co-optimization in EDA. Jason has been a very good friend for more than 30 years. He is currently a endowed name professor at UCLA Computer Science Department, and also the director of domain-specific computing center, which is a very successful center. I myself was part of the center for a period of time before I moved to Hong Kong. And Jason received his PhD from UIUC, and since then joined UCLA, developed a very successful career there. He is a very distinguished researcher, an educator, as well as an entrepreneur. He made a very fundamental contribution in physical design and found a company acquired by Magma, right, early days. Then after that, he found Auto ESL, a high-level sensors company acquired by Xilinx, which I think the tool, many of you, if you do FPGA, you must have used it as well. And he has a number of accomplishments, received numerous awards, including a member of U.S. National Academy, and fellow of IEEE, fellow of ACM, and member of U.S. Academy of Inventors. There are also a few other major awards from IEEE, as well as SIA. He received the SIA University Research Award, the EDA Achievement Award, and most recently the IEEE Robert Noyce Medal for his fundamental contribution to microelectronics. And IEEE Medal is the highest level recognition within IEEE, which is the largest professional organization in electronics. So I think with all this distinguished record, we're really honored to have him coming here to give us a talk. Some of you attend the SS talk he gave a couple days ago. And when Jason was very nice asking whether he should give two different talks or the same talk, I humbly request he should give a different talk. So he kindly agreed. So I'm very excited to hear another very exciting topic he's going to share today. Jason.
All right, Tim, thanks for that kind introduction. Indeed, this will be a different talk, the different topics. But nevertheless, it has something to do. All right, so this is probably better. It's for the recording. So this is all related to electronic design automation. I don't know whether I need any explanation about what it is. The team mentioned that this Robert Noyce medal that you have to, like an Oscar moment, you have to walk on a stage, give 1 minute acceptance speech, and then walk down. So I was debating what should I say to tell them about my work. And so I tell them this story, that this wonderful couple, one of them is a very successful real estate developer. He doubles the property every 12 months, 18 months. And the other one is a very successful interior designer, and he would decide, or she would decide the carpet, the wallpapers, and all the decorations. And a lot of people envy this couple and how successful they are. In fact, the interior designer has a terrible, terrible life. You can imagine there's the rooms to be decorated doubles every 12 to 18 months, right? So it's a very demanding job. So in our language, the real estate developer is now our friends in electrical engineering, double the number of transistors every 12 to 18 months. And for people who design circuits, and these are the interior designers. Who is going to buy a bag of transistors from electronic stores? No one. You want to buy functions, right, to do calculation, to do web serving, and so on and so forth. So now our job, the EDA, is to, I told them, is to make the life of these interior designers that easier and more productive. And so exactly that's what we do with electronic design automation. So for those of you who work on electronic design automation, it goes through a flow. By the way, it's a miracle that we can design 100 billion transistors that within a matter of a month, right, a few months. But we go through many steps. We start from system specification, and then we go through high-level synthesis, logic synthesis, technology mapping, and then the physical design. The title talk about the space and time. Can someone tell me when did you decide the space of your design? Which transistor goes where, in which step? Physical design. When do you decide the time dimension? Which calculation happens in what step? When do you make that decision? High-level synthesis, thank you. So, so these two are two extremes of the whole design flow. So first you do scheduling, resource allocation, resource binding. At that time, you already decided which operation happened in which clock cycle, where. And then you synthesize that circuit, you optimize, you map it to a particular library, right? For FPGAs, you map it to lookup tables. So for ASIC, you look at whether I go to TSMC 14 nanometer and or 7 nanometer, and then finally you do the place and route designs to put them on a two-dimensional surface, or maybe three-dimensional surface if you are doing 3D IC designs. So why they have any connections to do that? So that's the topic of my talk. And in fact, there's a lot of opportunities I want to convince you if we can think about the space and the time together to optimize. Three things I'm going to talk about. One is that physical high-level synthesis with physical planning. The second one is systolic array synthesis. The third one is layout synthesis for quantum computing, where you have to think about the space and the time simultaneously. Since the team says let's avoid overlap the two talks, that the systolic array I talked about on Tuesday at the Access workshop, I will skip that, but let me tell you the high-level synthesis and then the layout synthesis for quantum computing. So first, by the way, I started my PhD in physical design. So my master thesis was on multi-layer channel routing. In physical design, after I joined UCLA, the first project I did was try to do interconnect optimization. Because the reason we care about that is right around the 1990s, the VLSI design goes through a critical transition. Used to be the case, you just count the number of levels of a logic. You have fewer levels, you have a faster circuits. However, around that time, there's a transition is that the interconnect delay is longer than the gate delay. That you have to know, for example, on the curve there, I showed you that the 1 millimeter lines is already in the order of gate delays. If you look at the 2 centimeter lines, which corner to corner on the chip, so it's much, much higher than the gate delays. So you have to think about how to optimize the interconnect, not just optimize the logic. So we did a lot of work in 1990s. For example, we decided how to decide the topology of your net, right? Do you use a Steiner tree of what shape? That you use a star or use a spanning tree, or we have some concept called the aberrations, right? Rectilinear aberrations. So we have this sequence of work. So we come up eventually an interconnect-centric design methodology. Used to be the case you design a logic and worry about interconnect. We says no, if interconnect's the main character, you design your interconnect first and you design your logic around that. So that was 1990s. But when we come down to the decade of 2000, I basically give up. I think we lost the war. Because of continuous scaling, there's no way we can make sure that to optimize all these interconnects so that we can cross it in one clock cycle. So this is a study we did very early on in the year 2000, maybe 2001. We showed that in a 7 nanometer technology, and you have a 5 gigahertz clock, you already need 5 clock cycles to go across the chip. So it's impossible to do it in 1 clock cycles. And of course, that we are now at 2 or 3 nanometer technology, so things is a lot worse. So this is a TCAD paper we had in 2004. So what should we do? So then we decided, if that's the case, then we have to think about how do we manage. When do you cross the chip in what clock cycles? So that, because the timing is decided in high-level synthesis, so we have to combine physical design with high-level synthesis. So at that time, we came up with this idea of RDR architecture, regular distributed registers. So in this architecture, you can look at each one. The LCC stands for local computational cluster, and it has a whole bunch of adders, multipliers, which you need to do, for example, neural network computation. You have a finite state machine to control which clock cycle does what. But more importantly, I have these registers, files. They hold signals for different number of cycles. So, for example, the first set of registers that hold the signal for 1 cycle. Then the second set of registers, they hold the signals for 2 cycles. And another set of registers, they hold the signals for example, k cycles. K is the number of cycles you goes across the chip, right? So that I physically schedule it so you can go it cross the chip in multiple clock cycles. So that's actually, for example, that's the one, the furthest across the corner. We'll use it, we'll have this register hold the signal for a number of cycles. So, and then to design something of this kind, then you really need to change the flow. It used to be the case of water down the water flow, right? You start from scheduling, then you do synthesis, you do physical design. So now we actually will do this layout, we'll do scheduling-driven placement, because I have to figure out which one goes to which register files, depends on the number of cycles you need to communicate. And after that, I will do a placement-driven rebinding, rescheduling to optimize. So that's actually the iteration I have. So that was the idea back in 2003. But however, it didn't quite work. It really worked. We have publications, so a PhD student graduated in this, but it did not get a wide adoption by the industry. So that's, by the way, is the ultimate test. You can have a thesis, you can actually have a set of papers, but after a few years, you have to ask, maybe tens of years, has that been used? So the idea has to wait for another 17 years for that to be adopted. And it's going to be not exactly the same of this idea. So what's the problem? The problem is that first we're using this high-level synthesis engine we developed based on this compiler out of Stanford. It's a good compiler, but it's not very robust. Not all the designs can pass, so that's already a problem. But the second one, maybe a bigger problem, is that remember I have the registers hold signal for multiple clock cycles. We did not consider you pipeline the interconnect. You can actually have it, the registers in the pipeline. And also this regularity, having that regular structure is nice, but it has more overhead. So this idea has to wait for another kind of a 15, 20 years to come back. But in the meantime, what do? We develop, first thing we want to overcome all these limitations. We developed a very robust and scalable high-level synthesis system in a kind of a decade of 2000 to later part of the decade 2000. So that's where we noticed there's a compiler, unknown compiler out of Illinois called the LLVM. How many of you have used the LLVM compilers? Okay, it's good to see many hands. Most likely a modern compiler classes is taught on top of a LLVM. So it has this idea of life cycle continuous optimization, right? It's a compiler infrastructure. So what we take that, and then this is also the compiler infrastructure a lot of the industry are using. For example, all the Apple C++ compilers right now is based on LLVM. So instead of generating, for example, x86 instructions or ARM instructions, after the first part, then we'll generate the customized backend. We go through scheduling, resource allocation, we generate VHDL Verilog. So that was a very successful project, and so the system called XPilot, later on called Autopilot, that's the spin-off because a number of companies want to use that. So eventually Xilinx acquired the company. Other than the LLVM-based compilation, for example, there's a number of other things. One thing I will mention later on is the SDC-based scheduling, system of difference constraint. My former PhD student, Professor Zhiru Zhang, now he's a faculty member at Cornell. That is a big contribution from his thesis. So the qualitative result can match or exceed manual designs. So this is all documented in this keynote paper from TCAD, April 2011. That's also the year the company got acquired by Xilinx. They did a whole bunch of due diligence. And after that, I encouraged them to publish the result. So Tim mentioned that how many of you have used Vivado HRS or Vitis HRS in your class project or research? Okay, so good to see many hands. So this is a screenshot I had early this year. So I already exceeds the 10,000 citations, right, Vivado HRS. But there are challenges that for some of you who are doing design, that you will find out there are two challenges. One is that, for example, we're using systolic rate design for CNN acceleration. It works well initially. But however, as you scale, for example, now our frequency start to be 250 megahertz, but when you increase the array to be 13 by 4, 13 by 6, 13 by 16, it drop almost by a factor of 2, get down to 170. And also, the runtime is horrible. For those of you who are in a rush to submit a paper to that FPGA or to DAC, you know that you have to literally wait 10 hours, 15 hours to get the place and route to finish. So the scalability is a problem. And then you will ask the question, why can't we just parallelize? And if you look at the parallelization rate, it's very low. We turn on multi-core compilation. After 2 or 3 threads, there's no difference in the runtime. It's still many, many hours. It did drop from 25 hours down to 15 hours, but that's it. And you can see the core utilization kind of goes around between 2 to 4. Why can't we have higher parallelization? So what's the problem? If you take a closer look, in fact, there's a lot of challenges to design a modern FPGA. The modern FPGA is not a single die. This is, for example, U250, U280. U250 is a very large FPGA, has 4 dies, right? And on the silicon interposer, it's a 2.5D design. U280 has 3 dies. And then they have a lot of pre-built IPs. And this DDR controller is either at the middle of the chip, and then you have the PCIe IPs to talk to the host at the boundary, right? So these are fixed locations. And then if you are using HBM, high bandwidth memories, it's actually all at the bottom. That takes almost half of the die. So when you write RTL code or when you write high-level synthesis code, you have no idea where your logic end up to be. And then if you have to talk to another logic, goes across 1 die or 2 dies or 3 dies, the timing can vary significantly. That's why when you have a small array elements, if it's in 1 die, that's fine. But at the moment it goes through multiple dies, it can be losing a lot of power. So I show you this simple case that you have a full and the bar being 2 functions, and they can be far away. But in this case, in order to hide the delay, you got to insert some buffers or pipeline registers. But when you write the high-level synthesis code, you have no idea where they are. So, and then if you give it to downstream place and route tool to do, because remember this is a separate, because you didn't do anything in the scheduling, resource allocation, When down to physical design, Xilinx tool try very, very hard to pack all of them in one die to avoid this cross-die connection. But then that creates another problem, is that you have a lot of local congestion. A lot of time routing just failed. You cannot even get a design. So that's the problem, right? So here, and then you can manually iterate. You can insert some pipeline registers and so on and so forth. But this is very painful optimization problem. So high-level synthesis definitely works, but when you do really large designs, that's a challenge to scale. So the breakthrough come in, as I said, from our initial idea, takes another 17 years to early 2020s. The idea is actually very simple. You do high-level synthesis. When I write a C code, I have no idea which logic goes to where. But then I can go through high-level synthesis. I can generate the RTL code. Then I can do a coarse-grained floor plan to figure out which one goes to where. Once I know the floor plan, then I know which wire takes long time to communicate, need multiple clock cycles to communicate. Remember, I'm going to synthesize, so I'm going to decide how to change the finite state machines, or how do I change the pipeline structures so that all of its actual clock cycles can be accommodated, and then I can still have a very high frequency. So that's the whole idea. You can see that you write your program into a number of modules, and then I will do, for example, iterative partitioning-based placement. I place them into regions. From these regions, I can estimate delay from one region to another region. Once I have that estimation, I can figure out how many the cycles I want to add, and then I can do the necessary pipeline of the interconnect. So this is the idea called the auto bridge. I think this work got the best paper award at 2021 at the PGA symposium. However, there's one the minor detail you have to address. If I give you a data flow diagram, you know those two edges takes more cycles to cross. So you insert registers, and is that going to be correct design? Is it going to be a correct design? You insert some pipeline registers from 1 to 2, 1 through 3. It may not be the case, because all these signals coming out of 1 has to arrive at a signal at 7 at the same time, right? So if you delay some of the passes, you have to delay the rest of the passes. You cannot selectively doing that. So this is correct, because out of 1, you delay everything by 1 cycle. But here, that you have to be careful that you could actually delay after you insert all these actual registers, then it's actually correct. So all of them delay by 2 cycles. But in general, how many should I delay per connection? And also, how do I decide that? So this is actually a mathematical optimization problem. So we assign a variable SV for each vertex. It's basically like a sequential arrival time. And then for each edge, SU minus SV is no less than additional latencies needed for this edge, right? So, and then the whole idea is that we want to minimize the area overhead. So the problem is to figure out how many should I insert so that I delay the arrival time of signals sufficiently. So xi minus xy represent the latency of all the paths between vertex x and vertex y. So just give you one example that if we have this system and w equal to 1 means that the width of the 1, right? So here that S2 has to be larger than S1 plus 1, because that edge, I have to add 1 extra latency with delay. All others, I have no requirement. I just say S4 has to be larger than S3, and the S3 has to be larger than S1. You just add this precedence constraint. All of this, you write it down. And then you want to minimize the registers inserted, so you have to say S2 minus S4, S1 minus S2. You add them all together. These are the actual pipeline registers you're going to have. So you minimize this objective function. Does it make sense? And feel free to interrupt if you got lost. So you have a set of linear constraint, and then you have a linear objective function to optimize. What's the problem formulation we have here? Linear programming, okay? And definitely it's a linear program. Any other comments or additions? It's an integer linear programming, right? Someone says, because all these S tell me that how many clock cycles to get to this node. It has to be an integer because it represents the number of cycles to get there. So this is so-called integer linear programming. Integer linear programming, is it the easy problem or difficult problem? It's actually a very difficult problem. It's an NP-hard problem, so you cannot have the exact solution. But however, the way I write it in this way, so if you rewrite it, it becomes S0 minus S1 less than 0, S3 minus S4 less than 0. You can see each equation has a pairwise difference. So that's what I call the system of difference constraint. Once you have this formula and the underlying matrix, you can prove it has so-called total unimodularity. And then the whole problem can be solved using linear programming, and it's guaranteed to have optimal integer solutions. So that's very significant. In fact, this is the same optimization we did in the scheduling as well. So for those of you who are running Vivado HRS or Vitis HRS, now you know the secret algorithms goes behind that the scheduling is solved using this system of different constraints. And then you can add more constraints to approximate solution. So this is very effective. So for example, remember that the original design that is around 350 or 370 megahertz. If you don't do anything, it'll drop below 200. Now with this, we scales very well and continue to be over 350 or something. And then this one optimized average is 335 megahertz. And if you don't do anything, it drops to significantly lower. And then otherwise drop to 223. So the resource constraint that the overhead we have is very small. So that really, because all you need to do is to add some pipeline registers for the interconnect. So this is a fairly large syslogger design on an FPGA 24 by 24. So if you want to, because the idea is you want to use up all the FPGA resources for acceleration. Just give you another case study. This is stencil computation. You use it for image processing. You use it for some the high performance computing problems, that especially PDE, partial differential equations. You have to solve one point based on the nearby points. You iterate. You can see also the Vivado result goes up and down, but we can really maintain the performance. So it's a secret weapon for us for a while. Every student in my lab is using this set of tools because the difference is the paper get accepted or rejected because there's a factor of 2 performance difference. Now we make it open source, so you can all download and use it. I know Professor Wei Zhang's group used some of these, and they are also improving this result. So for performance, now we can, I think that's the frequency. That frequency we know by optimize space and the time together, we can have a significant improvement. And then the second problem, remember I showed you, is this compilation problem. Everyone's complaining. From small array, it's fine, takes less than an hour, and then all of a sudden it goes to 15, 20 hours. And a common question people ask is that, why can't you parallelize? I have 64 cores. Right, I have 128 threads, then why can't we parallelize? Why can't we parallelize? Is it easy to parallelize placement? Is it easy or difficult? It's hard, because otherwise this will not be a problem. The problem is hard just because timing is a global problem. So you can take your circuit, you divide it by 4 by 4, that being 16 pieces, right? But the critical paths can go from 1 to 6 to 7, to 8, and to 12. So if you optimize each region independently, you have no idea what's going on in other regions. And as you shorten this path, some other path becomes longer. So you cannot separate that, optimize independently. But because we did this space-time optimization, remember, because I added these pipeline registers when you cross multi-dies, now all of a sudden, each piece of a circuit within each region is isolated. They don't have any path goes to another region, because if they go to another region, this is considered to be long interconnect. I will insert a pipeline register to cut you off. So then you end up to the case, and I only have circuits that confined in each regions. So now I have the flexibility or freedom to decide how big or how small a region I have, how many I should have. So in our case, we can easily get, for example, this 2x4 8 regions, or we can get 16 regions. That you don't want it to be too small, right? Because you will introduce all these pipeline registers. So we have that, and we separate the place and route into slots. Now we're in business. We can optimize each slot independently, right? So it was never possible. This is by considering space and time together. So this is actually the circuit. So you start with a data flow diagram that you have multiple PEs that communicate through FIFOs. And then you we will partition them into a few regions, and then we have boundaries that are separated by pipeline registers. Now each region can be placed and routed independently to its own physical region, right? And then I put the chip together. So there are a few things we have to do together. So here I insert so-called the pipeline registers. You can also call that anchor registers. And here I will do each island place and route independently in parallel. And then finally, I have something to stitch them together. Unfortunately, this is in collaboration with Xilinx. They have an open source tool called the Rapid Write. So they can take solution from different pieces and connect them together. This actually is another Best Paper Award. So the students are quite amazing that Li Chengguo, he got 2 Best Paper Award that are back-to-back because this is a sensational result because right away you get 8 to 10x improvement. But it's not totally trivial. You have to figure out a few things. One is how to align the interface between the island. So you do this island and that island. Each one can be placed independently, but they have to connect them together, right, through these anchor registers. So there's a question, is that do you place anchor registers first, and then you do every region or island, or you do island first and figure out the anchor registers? So I think we end up using a kind of an iterative approach that you do it through a few iterations. And then the clock is the issue. That the clock, you comes in, and you want to make sure you get to every region that at the same time, because you want this to have 0 clock skew. So we have this. And then finally, we have to assemble all the partial result together. I mentioned using this rapid write, but there's also some complication to make sure the timing information get propagated. So all these details you can refer in our FPGA 22 paper, but this is a high-level idea by actually optimizing these each regions independently in parallel and deciding this space and time I can optimize it. So you can see this is the result we have. This is the rapid stream result, and so that's called the name of the tool. And then the middle one is that you just don't do it. You do Vivado with the pipeline RTL. So Vivado knows nothing about it. You just give them a pipeline RTL. It will still take a long time to do place and route. And the other one, this is the original one. You can see this is the runtime bar. It's dramatic reduction, right? And then the better news is that you do this, and it's very seldom you get the improvement, both the quality and also the runtime. A lot of time it's a trade-off, right? If you want to be fast, you sacrifice some performance. So in this case, that the frequency get higher, and also the runtime also get lower significantly. So that's actually a big success. So this is the evaluation. We have 20 core systems. Now you can see the number of usage of a cores has changed dramatically. It goes up to 80 cores, and in many cases, the phase 3 is the final stitching. You don't need everything to be active to get done, but in the middle portion, we use a lot of cores. So you can say that's exciting. How do you use it? The key to use it is that you want to create a data flow design style. But it's very easy. The simple extension is that we have a system called the TAPA, allow you to describe a data flow-based high-level synthesis design. So the key difference between data flow versus non-data flow design is that every module in a data flow design, I communicate through FIFOs. So I write data into a FIFO, you read data from a FIFO. What are other possibilities, for example, you can do? How otherwise you can communicate between different modules? Yeah, you can communicate through shared memory, right? For example, right? So, or some double buffering, and so there's other ways, but we just want to standardize. You want to make FIFOs to the communication, and then so the code you can see is actually very simple. And you do this simple vector add, and you divide it into 3 different tasks. Why you need 3 different tasks, or maybe 4 different tasks? The first task is to do the add. You know, you need that, right? But then there's also a second task. Is basically is memory to stream. Basically, I want to read the data from memory, right? And then another task is stream to map, because everything I created as streams. So here, what I will do is that I invoke memory to stream A to this array A, and then you have the number of n, and then A-Q, right? And then I have this basically tells you that what's the local array. A-Q is the local one, and then the A is the original A array from DRAM. And then you have memory and stream B, and you have n elements to BQ. And then you just add AQ, BQ, CQ, and the size of n. And then you do a stream to map. You write it to the C array and the n time. So everything goes in a streaming fashion. And so that's very regular. Then all we need to do is that this basically gave us the graph we are going to work on, right, to do the scheduling, to do the physical planning. So we use the AutoBridge to do planning, we do pipelining, we do the integration. By the way, if you do this one, your compilation, even high-level synthesis is much faster because we compile each module independently using high-level synthesis. And all these FIFOs and the memory read and write, we generate RTLs for you. So that's actually very fast. And we don't require that Vivado to generate the monolithic designs. So we have this type-out library. So again, this is something you can download and you can use. As I said, all my students that are using it. So they give you a high frequency, rich expressiveness. I didn't talk about it. For example, it can also support the HBM. HBM, there's another headache is that it has 32 channels. How do you know that which one goes to which channel? So that they can take care of that automatically, and it's fast because of the parallelization. So you can see that in my group alone, we have all these publications doing stencil computation and systolic arrays. This is a sparse linear algebra, then the matrix vector, matrix multiplication. So this is all fully open source. You can download it to use it. In fact, the main author, he's so motivated to maintain that, he turned on this return offer from one major this Web 2.0 company. He has actually started his own company and maintaining. So there's a RapidStream Pro version, and you can support not only RTL design can support, not only HLS design can support the RTL design or mixed RTL and HLS designs, can be hierarchical designs, can target any devices. At the university, we write a paper, we pick a device, we demonstrate the idea. But then anyhow, so if you are interested to use either the free version or the pro version, you talk to them because they will make sure that it's actually available to academia free of charge. Before I move on, is any questions? So this shows you the idea of the space-time that optimization in traditional VLSI design.
Yes. Yeah, so I have a question regarding to some early pages of this talk. It's related to inserting the flip-flops between the graph to, you mentioned the linear programming problem. Yeah. So in that step, like we see cost function, in the cost function, we see terms describing the latency related constraint, but like I was expecting something like related to, for example, how when we partition the graph, we might want to see like each partition maybe have equal amount of content or logic stuff inside that part. We want to see them to be balanced because you showing another graph where like a complex design divided to different SLR dies. So we might expect that they have equal amount of content to be filled in, but like I didn't see kind of cost term in that part. Is that like omitted for brevity, or in that application we don't have?
Yeah. So it's a very good observation. So basically, when you partition the design to each region, you want each region to be more or less balanced, and also don't exceed its capacity, right? So that actually we have a different set of equations or constraints, but that's done separately from deciding the number of registers, because you don't have to couple those together. The first one is a more classical physical design problem. So you can use the ILP to solve it. We're probably using an ILP, but you can also use any other method, something like a min cut based placement. So that's actually can be done with or without equations. But that's a separate step. Yeah, that's a good observation.
Thanks.
All right. Okay, so let's move on then. Just tell you that after we done this in the decade of this decade, we're getting somewhat worried about whether the Moore's law scaling can continue, and so we're looking at the alternatives. And then quantum computing came up to be a very viable alternative. It's not going to replace CMOS-based computing completely, but there's a lot of progress. For example, now our work started by Google. They come to us. We have some qubits. We may need design automation tool. I think that's back around 2017. I says, okay, how many qubits you have? They said, we have 4 qubits. I said, 4 qubits, you don't talk to us. Why don't you just use hand to place them? They said, oh, well, we're going to double, redouble, the complexity is going to be higher. So indeed, in fact, this is work out of Santa Barbara, and Google acquired them and continue. So indeed, now they can come out with systems in the order of many qubits, around 100 or over 100. IBM's roadmap is even more impressive, and they started around 2017. You can even go there, right, to use. Now has over 512 qubits. And Rigetti is a small company. And then there's a trapped ion-based systems. It also goes into 3264 in our region. There has the advantage, their gate fidelity is very high. And then my recent collaborator at Harvard is that they have a neutral atom-based quantum systems. They are over a few hundred atoms, and I think the roadmap is go to thousands of atoms easily. And that is even in room temperature. I'll show you movies how that atom works. So I don't know how many of you knows anything about the quantum computing. If not, let me try to first give you like a 2 minutes quick introduction, and then we can talk about the space-time optimization problem there. So we all know that computer science, electrical engineering students, we deal with binary numbers, 0 and 1. And the quantum, they also have 0 states and 1 state, but it was more importantly, they have something called a superposition. That a state, a qubit can be that in these either 0 or 1, that a linear combination of that. And then once you measure, of course, it gives you either 0 or 1, but the quantum state can be in a superposition. And then these, that two superpositions, you can combine them together, then you get a 2 to the, get 4, for example. So think about it, you will have these become a 2 to the n, just become the base vectors, and you can be a superposition of any of this. So this grows very, very fast. And so that's where the power is. And one qubit that can be either 0 or 1, but that there's also this concept called the entanglement. If these two qubits are entangled, then you measure one, you will know the state of the other one. Doesn't matter how far or how close they are. And so this is the entanglement. They have the correlation. The reason it's so strange is that you can actually have the state. It's not decomposable, cannot be the product of any single states. So that's naturally entangled. And this result can all have been validated, verified. For example, this is 2022 Nobel Prize. It's all about about this discovery or the proof of the entanglement. So for quantum computer to work, that you have to write programs. Program is actually not much different from the assembly code we have. For example, you can have a number of gates, X gate, and H gate, CX gate, T gates. I will not go into the details, but the fact is that if you have these basic gates, and you can compute any functions you want. That is, you have a complete set of gates you can have. And then you have a device graph called a coupling graph. So this is a very tiny quantum computer from IBM, has 5 physical qubits, right? So there you have some logical qubits and the logical qubit gates to be applied to those qubits. For example, I have Q0, Q1, Q2, Q3. And then what you want to do is that you have to map this physical qubit, logical qubit to physical qubit. For example, I'm going to use this 4 qubits to do the execution. So that's actually a circuit of a small adder. And so the first gate, then you apply it to this physical qubit. That's easy. And so this gate, you apply to this pair of physical qubits. And this is a problem, Q0, Q3. Why is a problem? Because for quantum computer to work, you have this entanglement. They have to be adjacent. So these 2 qubit gates, in this case, Q0 and Q3, is not adjacent. So you cannot execute this program directly. What do we do? Of course, you can report to the programmers as program aborted and error. And, or is there any other way to proceed? Actually, you can actually still make progress. What you need to do is that you insert a swap gate. You change Q0 and Q1. And if you change Q01 and Q0 and Q3, now they are adjacent. You can apply that gate to this one, right? And then you can continue. So that's basically a physical, I call that a physical synthesis. You can see this is different from physical design. So I do have to figure out which place qubits goes to where. But I also have to figure out which one is executed at what time steps. So the space-time concept come out very naturally. And in fact, very importantly, without discerning those, I cannot execute a quantum program. So when Google talked to me, I says, well, maybe this problem is well understood. A lot of people has worked on it. I know. I look at the IBM has some papers, and Google already has some systems, and many researchers has papers. The first thing before you go into a research topic is to figure out whether there's any room for us to do anything new or different. So what we did is that we come up with a solution. we'll come up with a set of a circuit which we know the optimal solution, and the other do not know. We give it to every tool to measure the gap. Oh boy, so that gap come out to be very large. So it actually not a few percent. You can see the gap can be 5x, can be 10x, can be 20x. Sometimes it's even larger than 20x. So that's actually the challenge we have. So I said, okay, if that's the case, and this is actually not very large circuit, all the way to 45 qubits, right? And then you talk about the number of gates. You have 600 some gates. So it's a very complex problem because you have to consider both space and time. I said, okay, if that's the problem, then we're in business. Then all we're doing has been doing different kind of optimization, right? So we started a program called the layout synthesis for quantum computing. Why I call it layout synthesis? First is layout. You have to decide the two-dimensional space dimensions, which one goes to where. And it's also similar to high-level synthesis. You have to decide the scheduling, right? When you do what execution. So that's where the input is the circuit, and also the coupling graph describes the device. And then we have to decide the space-time coordinate of all the gates, and including the inserted gate. So first dimension is the time coordinates, which gate executed at what time. And then the second one is the space coordinate, saying which P3, that the Q0 goes to physical qubit P3. But after a while, you can insert a swap gate, and the Q0 go to P2. So that space coordinate you want to decide as well. So this is the swap gate. The swap gate can be implemented by a pair, basically by a triple lit of the CNOT gates. I will not go into details. So it's all achievable. By the way, my students can go to IBM system and run these programs after you have done this optimization. So what do we care? We care about the depths, basically how many steps I execute. And so that's the maximum time variable you have, right? And the swap count, how many swap gates I have, and then the fidelity. And then constraints, you got to execute all the gates and then respect dependency. So if one gate has to be executed after another one, you cannot jump ahead, right? So at that time, we look at it, there's really no optimal solutions. The one we come up with, we literally come up with space variables, time variables, and then we describe the constraints using the space-time variables. Give you an idea, for example, you have a time variable TL, means that the gate L will be executed at time T. And then you have a mapping variable pi QT, at the time T is a logical qubits, Q is mapped to physical qubit, that pi QT, right? So you can have a swap gates that will change the assignment, so then you will make the change accordingly. So this is actually a very efficient encoding compared to all other solutions. So this is just shows you the encoding that the mapping will have. They tell you, then you can have the constraints. So what are the constraints? The first one is a valid mapping constraint. If you have some variable that physical qubit and logical qubit Q at the time T goes to this P. So every qubit has to go to some physical qubit, right? So that's a valid mapping. And also valid time, all of them have to be executed within time T. The capital T is something we're going to optimize. And then if you have 2 qubit gates, and then this has to be the 2 mapped physical qubit have to have an edge to connect them. So you can describe using these equations, and the dependency can be described by the gate dependencies. So that's actually what we have. And then with all these constraints, we'll get to solve it by optimization problem. For example, how do you minimize the depths? Minimize the depths is to minimize all these maximum of all the time variables. Swap count, remember we have this binary variable to say at the time t, at the edge e, do I have a swap gates or not? So you'll summon them up to minimize. And then we solve it using SMT, something team is very familiar with, that the SAT used a lot in the, for example, formal verification world. You have Boolean satisfiability, but except in SMT, we can have integer variables. You can even have real numbers if you want. So it's very expressive. We find out that we can actually solve it, write down all sorts of constraints and solve it. In particular, we use this as Z3 compiler. I think it's an open source project. Some of these authors we were working with was from Microsoft. For the first time, when we have this result, we're able to solve optimal space-time mapping problem up to 20, 30 qubits. But there's challenges. You can see here it's doing well, 5 by 5, 6 by 6, 7 by 7, the number of gates, but it also goes up quickly. You get to close to 100 qubits, goes to, for example, 50 gates, then it can literally takes over a day to execute. So then I have another student come in. She looked at our formulation. She says, oh, we can do better. That not only a little bit better, a lot better. She improved it by a few thousand x in efficiency. So how do we do that? I'm sorry, that actually on the average is 387x, but there's a few cases get to over 1000x improvement. So now we can actually compile circuit up to a couple of hundred qubits. It's still a challenge. By the way, the physicist is making a lot of progress. I saw that we get to hundreds of qubits, we can rest for a while. And then the IBM just keep doubling their qubits very quickly. So we really have to come up with all the optimization. So we have some paper in submission goes to handle like in the order of 500 to 1,000 qubit region. Just tell you some ideas that some of you may want to do some research in this area, give you an idea of where the improvement coming from. So the first time that she decided, yeah, we want to do space-time optimization, but it turned out that some of these space coordinates that were for the gates is not necessary, because if I know the space coordinate for the logical qubits, if I also know the time coordinate, I can derive this space coordinate. So, and then these, for example, for a circuit with 30 gates on a 5 by 5 grid, we can reduce constraint by 24%. Remember, SMT or SAT eventually is a NP-hard problem. You are using some exponential algorithm to solve it. So if you reduce the constraint, you can, for large problem, you can get a lot of speed up. So that's actually by the better encoding. The second one is that we want to say that we have this type of constraint. We use at most that k elements that or variables to be true. This at most function that you want to use it, that basically be a set of Boolean variables. You have the pseudo Boolean solver. However, that's actually less efficient. If you know it, then we can use the CNF directly. CNF got converted into set solvers. Set solvers are better, faster than pseudo Boolean solvers. So that's get us another set of speed up. The first one I will tell you is that the variables can be encoded by different types. One is that we literally encoded by an integer variable. Remember, pi qt means that this says, okay, logical qubit q at a time t, which physical variable does it go to? So that gives you a number. But now we change it into a bit array. So we were surprised by this big vector that it's a huge improvement in the speed up. And then the third one is that how do we can use incremental solving. That we keep trying, can we meet this depth constraint? If we can meet, then can we reduce the swap count gradually? And then as we do it, we will basically do the search on the solution space. Each one, we can make use of the solution from the previous one. And then, so that's actually give us a very good result. So before we have this one, for example, you go to IBM Qiskit today, you are using this swap optimization procedure called SABRE. In fact, we have Professor Yuan Xie here in the school now. He did a little bit of work in this space. I'm not sure if he's involved, but he is a very close collaborator. Professor Yu Fei Ding is coming out of that group. It's a well-known work. So now we can see we can have, on the average, 70% depth reduction. And then swap count, we can reduce almost by a factor of 2. A more recent work was that out of, I think, Wisconsin, that using MaxSet, where you're reducing it by 62%. So the current focus in this area, where I want to support different topologies. For example, I showed you, everything I showed has been on this Google Sycamore device topology. IBM has an interesting topology. You can show you that it's used heavy hexagon topology, the Rochester architecture. And the Tokyo architecture is another one, and that's Ricketti's. But what's more exciting, so that's all superconducting technology. I was at the Google Quantum Summer Symposium, so I visited their lab. You have to this very deep refrigerators to cool it down. The neutral atom-based ones is actually very exciting. So these atoms, you can move them at the room temperature. Once you get close, that you can have this 2 cubic the entanglement. And then, so what we need to optimize is you can see space-time. You have to figure out where they should go to and what time when you have this exposure, that's the 2 cubic is being executed. Once it's all finished, you can see it goes to the upper corner. That's to do the measurement. So that's in a different zone, right? So this is a very exciting work out of Harvard. We have a joint project now, so we're making use of this. Where I did not talk about very much is that once we have an optimal compiler, we can do a lot of a what-if analysis. For example, we can tell Google saying, you have this architecture. If you want to do, for example, optimization to do max cut, you may want to add 2 more edges to reduce the depth a lot. Where do you add? We can tell you because we have this compilation tool. Same thing that here, that you can move things around by this AOD SM. We can tell you if you add another set of a laser, how much you can speed up the whole computation. So it's actually very important because for us computer scientists, we know that all these architecture decisions, for example, whether you use CISC, whether you use RISC, a big part coming from compilers, right? So both can be supported using the SMT formulation. But SMT alone is not sufficient now, so we often use some hybrid formulation. Mm-hmm. So here's the concluding remarks, and how I'm doing on time, team. So first, that I want to convince you, I first gave this talk back in March at the Physical Design Symposium, and the audience was all physical design researchers. And I said, you guys, me included, in fact, 20, 30 years ago, we focused mainly on spatial domain, space variables. And once I started working on high-level synthesis, I noticed the high-level synthesis guys don't care about the spatial variables. They care about the mainly time variables, scheduling, which steps will execute what. But however, there's much value to consider space-time co-optimization. Maybe I'm lucky. I trained as a physical design researchers, and after a while, I sort of get bored. I start working on high-level synthesis, and I learn all these tricks and realize there's better opportunities to combine all of them together. So before I end, I want to give you this quote. Time and space are modes in which we think, not in which we exist. Another question is, who said this? Don't go to Google. Just who said this? Huh?
Kant. I mean, a German philosopher, the Chinese is Kant, I'm not sure.
Kant. Any other guess? Because this is talk at the IAS, I thought it's appropriate to get a quote from Albert Einstein that was in the other IAS, and he's devoted most of his time looking at the relationship between space and time. So I think there's a lot of truth, and we should unify these variables together. That he's thinking about the big problem in the universe, but small problems on VSI chip, there's a lot of opportunities as well. With that, I want to end my talk and acknowledge the high-level synthesis team and the physical design team and the quantum computing team. Thank you.
All right, thanks, Professor Justin Huang, by taking us to the journey from the EDA on the conventional FPGA to the quantum computing. So we can take some questions from the audience. Please raise your hand.
Hello, Professor Song. Thanks for the inspiring talk. So I get the impression that the co-optimization speed up from by co-optimizing the space and time is like a reformulation of a problem, like you find in the quantum case you formulate to the SMT formulation. So is that the most will give you the most speed up? Just do some problem rewriting, and how about we accelerate after the problem formulation, the solver itself? Is it worth to exploring that direction also?
Oh, definitely. We are very interested to see the work to speed up solvers. And first, we will treat the solver as a black box, and then we just trying to come up with better formulations, doing incremental solving and all these things. But now we are also very interested in improving the solvers. So I have a few students in my lab working on, for example, we start from SAT solvers, want to improve the speed of that. So we're very motivated because we are suffering from the kind of this complexity of the solvers.
Yeah, and a related question is that since I also do a lot of FPGA synthesizer and PNR, I just wonder, since we have the accelerator right at our hand, so why the Xilinx tools don't have the hardware accelerated solver for all the EDA algorithms? Then when we do the FPGA design, we just fire up the FPGA to calculate its own placement and route.
Yeah, so that's an excellent question. But I think that before they go with hardware acceleration, they probably should just try to make use of a parallelization first, right? So before that, because they were even multi-core, they are now utilizing it very well. You can do a study of all different kind of accelerators. This is our experience. You have to have parallelization that explore first, and then you go further specialization. If there's absolutely no parallelization opportunity, it's actually also very difficult to accelerate, right?
So the last question is do you think it's possible in the future we have this kind of FPGA assisted EDA tools?
Yeah, definitely. So in fact, there's one very well-known company. I forgot what was it. That's the OPC, optical proximity correction. So that simulation, this is all done on a FPGA set of systems. The company was bought by ASML for $300 million. It's a very successful company. So you can definitely do that. And in fact, the founder or co-founder, I know him very well. I understand he has a PE fund in Hong Kong that a number of years ago. I haven't talked to him recently, so that's possible. Think about it. Another good example, you do circuit simulation. It's very, very slow. So a better way to do it is to do circuit emulation. That's all done on FPGAs. You go to Cadence and Synopsys, you buy this big box, very expensive, but it's basically hundreds of thousands of FPGAs to speed up circuit simulation. So it's already being done. It just had not been done on that place and route systems yet, but on circuit simulation, it's definitely done in some of these optical simulation. It has been done before. And you have to say GPU is also very powerful, very promising. So there's people, and it's easier to program in some cases. Before you go to FPGA, maybe you want to do figure out whether you can do it on GPUs first.
Thank you.
That side, yeah.
Thanks for your talk. And my question is, I noticed that in the cross-die cases, you insert registers to address the timing issue. But my question is, how to determine how many registers to insert to solve this problem? Because I noticed that in some academic research, we observed that they insert the registers aggressively. But it will lead to array increasing. So how to determine the number of registers to insert?
Yeah, so typically you want to do it in a multi-die cases. Before you leave the die, you want to do a one register. And you could, maybe that's sufficient. If it's not sufficient, before you enter the other die, you want to insert another register. So in many cases, that'll be sufficient. But if the region within the die is also very large, you can actually insert more, right? So it's not very many.
So you have an analytical model to know which signal. I mean, if this signal is very, very far from the die boundary, you need to insert many registers.
Not many, but maybe you need to insert more than one.
Okay.
Because our region is not very large.
Okay, I get it. Thank you.
Yeah.
Question from the back side.
Thanks, Professor, for the interesting talk. So I'm interested for the quantum EDA because I think if we considered like for Rigetti processor, they have this coupling graph. For Google, they have this coupling graph. But I think like for quantum processors, it is quite complicated because like its qubits are very noisy, and then maybe some qubits are better than the others, and then there are many physical factors. And how will you deal with this in the optimization?
Yeah, so that's a great question. So I'm simplified the problem a little bit. For example, I showed you how to minimize the depths or how to minimize the number of swap counts. But you can also minimize fidelity directly. So that's actually probably the most important near-term goal, because each qubit, right now they can get to 99.9 in our range. That for single qubit easily, but if even 2 qubit gates, you can get to that range, 99.5 to 99.9. So, but that's compared to CMOS, that's very poor, right? That accuracy. So you do want to improve, but you can model these fidelities as part of either the constraints or objective. For example, you talk about indeed the different qubits and has different fidelities, and the changes over the time. They do calibration, and then when we do the mapping, you can take that into consideration. So you can put it into the SMT formulation. And we did not, I did not talk about it, but it can be done. Right.
Thank you, Jason, for another very exciting talk. For the inserting buffers, it's really interesting. I think allow parallel physical design. But it remind me, early days there were technique called retiming, which is adjusting, inserting buffer for slightly different objective. So I'd like to hear opinion that what's the correlation of these techniques with retiming, because that's one is for performance optimization.
Right.
And it doesn't address many of the physical design issue.
Right.
But there seems some that also formulated as linear programming at the end. Right.
Yeah.
So I'd like to hear your opinion.
Yeah, Tim's question is that what's the connection to retiming? It's an excellent observation. It's very closely related to the retiming. What happened with retiming for students who do not know the problem is that you write RTL code and you already put in some registers, but these registers can be moved around, right? So that you buffer the register, you have the register here, you do a gate, and you do some more gate, and you can actually move this register between these two gates. So the retiming, you can do all these tricks with the constraint. You cannot introduce new registers. So because you can introduce, but you cannot introduce extra cycles because RTL is cycle accurate. You described what computation handle what. So very early on, I showed you this 2001, 2003 papers. When we started high-level synthesis, so that's our goal. We said so we can be better than human designs because we can introduce all these extra registers. And then in fact, we can get a higher frequency design. So that's why motive is to consider this multi-cycle communication and all these. So the high-level synthesis, because we generate the finite state machines, we generate the circuit, we have the control how many stages you can go. So I had Bob Brayton, we had this long discussion during GSRC. He has exactly the same concern. He says, no, you have this loop delay ratio, you cannot break that. I said, yeah, that's true. That's for retiming, but for a given design. But if we can come up with new designs, we can do, which every time that I want to do this, I basically give you a new circuit, and then we can do retiming. So we are just playing with a much larger solution space with high-level synthesis.
Combine these two, because I think retiming to some extent is to rebalance the pipeline.
Yeah.
When you insert each circle, each node, in terms of timing, which before you do more detailed physical design, you really don't know the exact timing. So what you be able to combine what you have with retiming, because you're playing with the register placement, basically the insertion and the placement, if I simplify the concept.
Yeah. So that's totally possible. You can go further combine. So the way we did not combine is that we will just want to make use of the downstream tool as much as possible. So we control it at the module level. Each module is still done by, for example, Xilinx logic synthesis, place, and runtime. I think in that tool, they all have some retiming capability, either retiming or useful skill, right? So they play around with that. Yeah, so that's all there. We just didn't touch that because I think if you design something from scratch, you probably want to control all these knobs, but we are not doing that. We add a layer to their tool. Yeah.
We can take two more questions.
Hello. Thank you, Dr. Zheng, for the amazing speaking. And I actually have two questions I want to ask about the interconnection and the TAPA. So the first one is, in the, for example, the U280, there are three superlogic regions. When you do the data flow crossing the superlogic region, the timing usually would be kind of hard to optimize in a very high frequency. So we actually have some kind of project we are doing in the kernel in RTL code. And when we build this RTL kernel across this superlogic region, we want to send the data through this all the dies, but it turns out the timing will be really bad. So our optimization strategy is to use some IP core called ASI register slides to add register to on the boundary. So when you're doing this kind of data transition to the different superlogic region, you can have this register slides add on. But then we found out it doesn't really help too much about the timing. I mean, because from SR region 0 to SR region 2, the cross length is very long. So we basically try add another interconnect kernel on the SR1 region to translate the data. But it turns out that the timing issue still exists in a very kind of high frequency. So I saw you in your Tapa design there, you add some like your red bar is like a FIFO or register there, and you don't even need an interconnect on SR region 1. You can directly have very good timing results from there. So I just wondering how do you actually accomplish that in more detailed?
Oh, I'm pretty sure we have to, if we cross multiple SR regions, then we have to insert some within those regions as well, that if necessary. That depends on the frequency. But if you have no logic, maybe it's possible from SR boundary to SR boundary, you can go across. Right, so whether it's just pass-through or you have some more logic going to that.
Oh, okay.
Yeah, maybe the picture I shown you just a pass-through case.
Oh.
Then that's still possible. But if you do some computation in that and you go further, you probably have to also register.
So in the pass-through case, do you recommend more, like if we want to make the project have better timing, will be adding more register or using some FIFO to do the inter?
Yeah, so that or we can constrain the region size, so that the region size we can cross in one clock cycle comfortably.
Oh,
yeah,
okay.
Because we decide that, right?
Okay, thank you. And the second question is Tapa also working for since we are working basically building our kernel in RTL, so it's Tapa also can interact with this kind of RTL kernel, because in our current design, we basically just using Vitus HRS to do the host control to our RTL kernel. So I'm wondering if we want to use Tapa, it can also.
Yeah, so that Tapa itself, our research project, the open source version, I don't think support the RTL, but this Rapid Stream Pro, they does that exactly. So they support either RTL or HRS or even mixed design. So we have this need, we see this need, but the student has 2 best paper awards, he wants to graduate. But he's continue to, has a small team to enhance that. And if you're very interested, you should talk to them. And we are already using this Rapid Stream Pro now to do some of the project.
Sounds exciting. Thank you.
Okay.
All right. One last chance. Any more questions? Yeah.
Yeah. So one technical. So the first one is just a little technical question. You mentioned like you can tell IBM like if you want to add another edge in quantum circuit, I can predict like what edge to add. When you mention like this kind of suggestions to be made, is it based benchmark or analytic based? I mean, benchmark based, I mean, it's like you have a set of problem set, and then for each of them, you enumerate all possible edge to be added, and you just find which one will have the biggest effect, and then you say that's a recommendation, or you have other ways that is more analytical or theoretical to make such suggestions.
So yeah, I guess you refer to this quantum architecture optimization,
yeah.
Right? So the idea is we introduce some extra connections or extra couplers. And at the beginning, we indeed try this enumeration where to add it. But later on, I have a student come in and says, okay, I have a better way of doing that. You can encode those as variables in our SMT formulation. So the same formulation give us a space-time mapping and also the variables that if you only have 2 extra edges, where they should be. So it's actually a very elegant solution. So you go to my website, we have a page we organize into different projects. That one project is on quantum compilation, quantum architecture optimization. So you can read that paper.
Okay. Yeah. Okay. Thanks. Another is like just want to know your comments on, because like that kind of solver, exponential time solver is not scalable or sustainable anyway, because like the quantum number of quantum gates are going to grow at least like double every few years, and in that way, there will be an end in the near future that any exponential time algorithm will not work. And how do you think about like what's the?
Can you repeat what's the question?
Okay, so currently we are still it seems that we are still using exponential time optimal servers, this will not be sustainable anyway, because the number of quantum bits is going to increase. So after this stage get passed, when we have more quantum qubit, what's the direction for this kind of quantum bit mapping problem?
Oh, actually, I'm optimistic. I think we probably have done enough work already, although they will have more qubits, because the next step is to do fault tolerant for computing. And so you do need to do error correction. Once you do error correction, it's very expensive. You need 1,000 physical qubit to encode 1 logical qubit, something of that scale. So then problem complexity reduces 1,000 to 1. So when I have 10,000 physical qubit, there's only 10 logical qubits. So we are totally capable to deal with that. There are some more efficient encoding algorithms, but you are still talking about probably 50 to 1. So eventually, I think we have to deal with logical qubits, not the physical qubit.
All right, thanks, Professor Hong, again for the insightful talk.